Okay, welcome back. So last week we were talking about switch instruction. Compare core, right? So we talked about the core instruction. So this is on the x86 architecture to make some function call. So this instruction basically does two things. One is push the current code location, which is whatever in the EIP register onto the stack. And the stack is pointed by the ESP register, and then perform an unconditional jump to the code location indicated by the instruction. So the instruction may take a label as the operand, and the label will be compiled into something concrete. So it will be a concrete address at runtime. It can also be a register. If it's a register, which means before running this instruction, you don't really know where your target is, right? So if it's a register, that is called an indirect call. This one is called a direct call. So they have different security implications, which we will study throughout the semester. Another very important instruction related to the core instruction is the return instruction. It's like the reverse operation of the core instruction. And the core instruction is very simple. There is no operand. It doesn't take an operand saying where to return to, okay? So the return instruction will always pop whatever the ESP, the stack pointer points to. Stack pointer points to a memory location. So no matter what is at that memory location, we'll use that address as a target. So pop basically pops that address into the EIP, the instruction pointer, which means the CPU will keep executing at that address. So the target address in this case is in memory. Okay, because of that, if the memory is corrupted, the attackers will be able to manipulate where the CPU executes next. So that's why the return instructions are very important. We will actually learn how to exploit this next week. So a little bit background about the runtime stack. So in the algorithm design course, I believe you all learned what a stack structure looks like. In this case, we're talking about a runtime stack. It follows the structure of that stack from your algorithm design course. So at a runtime stack, it supports a procedure calls and also passing of parameters between those procedures. Procedure in this case is basically a function, okay? So stack is located in memory as well. A lot of what we're doing in this class is called read corruption attacks because we are trying to override some parts in the memory. Okay. So in most architectures, the stack goes towards lower memory. So this is the same for x86, for ARM, most architectures are like this. So when we push a value, which means we push something onto the stack, then on x86, the register to point to the top of the stack is the ESP. S is stack pointer. So it's easier for you to remember. E is extended stack pointer. So because the stack grows towards low memory, so when you push something, you are adding something to the stack, right? So when you add something to a stack, the ESP actually decrements, okay? Because it grows to a lower memory. When we pop something, ESP is incrementing. I will have some animations later to show you this. So in the semester, you may also see some other instructions. You do not see them very often, but depends on the compiler. Sometimes the compiler will generate instructions like that. So one of them is called enter. So enter, this instruction is equivalent to those three instructions, okay? The push EBP, move ESP to EBP, then subtract a number from ESP. So those three instructions as a group, they appear many times at the beginning of the function, okay? That's why Intel introduced a new instruction enter to replace those three. Okay, so it's just one instruction instead of three instructions. To make the CPU execute a little bit faster. Also, at the same time, save some space. The binary will be smaller because you only have one instruction. So the reverse operation of enter is called a leave. This one will release the function string set up by early enter instruction or those three instructions. And the leave instruction is equivalent to those instructions. Move the value from EBP to ESP, then pop EBP. The pop EBP here is moving whatever ESP points to in the memory to the register EBP. So just give you a high level view of those instructions. You don't have to remember them right now. Later when we say demos, when we say animations, you will understand more what's going on with. Okay, so that's our background knowledge for the x86, which is the 32-bit version of the CPU. Then now we move to the 64-bit a little bit. Most of you, the computers you are using right now, they are 64-bit, but they can still run the 32-bit program. So on the hacking platform we are using, you are going to exploit both 32 and 64-bit software. For a lot of IoT devices, embedded systems, they are still 32-bit, but they are not necessarily x86 architecture. Most of them are ARM, MIPS, and other architectures. So I actually showed you this picture before. So those are the registers available on the 32-bit and also 64-bit machine. The server we're using is 64-bit, but you can run 32-bit program there. So when you run 32-bit program there, you are only using a small portion of the registers, and also for each register, you are using just a part of that, right? So for the 32-bit, you are already familiar with those registers, EAX, EX, ECX, EDX. Those are the general registers. And in the 64-bit machine, they are extended again to RAX, RBX, RCX, RAX, RDX. And there are more registers from R8 to R15. Those registers were not available on 32-bit machines, okay? So on 32-bit machine, there's no such a thing as R8X or E8X, okay? It didn't exist before. So you can see from 32-bit to 64-bit, not only the registers we are getting bigger, longer, we are also getting more registers. Some of the registers that were not there. So let's look at our, I think this is probably our second example of the whole class. So last week, we look at one program, it's called the code add, right? That program was adding two 32-bit values together. Here we have a long add, which adds two 64-bit values together. So a very simple program. We have a main function. The main function has two arguments or parameters. The first one is argc. Arg here means argument. C means count. So basically, it tells you how many command line arguments are there. And the first command line argument is always the program name itself. Then it has an array of pointers. So array of pointer to strings. So it's basically multiple command line arguments, and each of them has an address, so I have a pointer here. So we have two local variables, long A and long B. So both of them are 64 bits. So no matter which platform you compile this, okay? You compile this program on 64-bit machine or 32-bit machine, the variable A and B, they will be 64 bits, okay? But if you do an int A, Then on 32-bit machine, it will be 32-bit. On a 64-bit machine, maybe 64-bit. So first, we check how many arguments are there. If there is only one argument, which means you do not give any input, then it will just print out the usage saying. If you give two more arguments, then what you give there are actually strings, right? Then you need to turn that string into integer in this case. Then you print out the size of lang on this platform. This one should always print out 64-bit, no matter which architecture it is. Then it converts that string you put in command line to an integer, to A and B integer. So we're using the first command line argument, now the zeros, the first one. So the actual first one will be arg_0, right? That's the very first one. That will be the name of the program. So the second argument will be the first integer, but when you type that, it will be a string. So we change that to an integer. We do that same thing on the variable B as well. Then we just add them together. We print out, we add them together using a function long and add. I did a little bit weird thing here. I use the address here because I want to show you what the compiler does there. The first argument, we actually use the address of A. The second argument is just the B, the value itself. So, and this is actually the computation part. We have a pointer pointed to a lang value. So we just add dereference that pointer, get the lang value, then add them together, and just return. Right? So very simple program. And if we go to our platform, you go to, I think I'll log in. Give me 1 minute here. Let me find my password. So if we go to, we find that challenge. Let's go for the 32-bit first. So L and 32. You click this button to run this challenge. So now we have this in the terminal. So you can say this is a program. So if we run this program without giving any command line arguments, obviously it shows us the usage. So if we want to add two numbers together, this is what we get, right? So you can see this is a 32-bit program. This is a 32-bit program, but the size of lang is also 8 bytes, which means 64 bits. Right? So then we add them together. So if we disassemble this program, we do an obj dump -b, then we do the machine, which is -m Intel. We always use the Intel syntax in this class. We do this, then you can find the disassembly of this program. Then we go to the long and function. So this is basically the long and function, and we can say we have 7 instructions here, right? So let's see what is the first instruction. Remember, in this syntax, the first operand, this column, this is the destination, and this is the source. So we are moving something to the register EAX, and EAX is 32, right? So what are we moving? So remember this brackets, they mean that we are moving something from the memory, okay? And the memory address is the register's address, ESP plus 4, okay? And how much data we're moving? We're moving D word, which is 4 bytes in this case. So we're moving 4 bytes from this memory address to register EAX. Then we're using EAX of the address. So this is like a dereference once from memory. Then we dereference twice using the address from EAX. And we're moving 4 bytes from EBX. Then after that, we're adding whatever is EAX points to EAX, move to EAX again. So here, these two instructions, those two instructions, we're actually moving 8 bytes from 2 adjacent 4 bytes in the memory to the EAX and the EBX. Then we add or ESP point to, which this is actually the variable A and its address, and this is variable B, right? And now we are moving whatever variable B is, but that variable is 64 bits, 8 bytes. But our architecture can only support 32 bits, that's why we're moving twice. But here we're not directly moving, we're directly using add instruction to add the lower 4 bytes of B to the lower 4 bytes of A, and the results get into EAX. Then you'll notice this instruction is a little bit different from this one. This one is an add instruction. And this one is ABC, means addition with carry. So it will use whatever the previous lower 4 bytes result. If there is a carry, we will use that. But then we add the higher 4 bytes together with carry. So it takes 7 instructions to do this simple calculation of adding 2 8 bytes of data together. But if we go to the 64-bit version of the same code, yeah.
Why do you need third moving DF to
Let me see if I have that on my slide. Which move? This one, right?
Yeah.
The reason we have that is we go back to the source code. In the source code, here we're not passing the value of A, we're passing the address of A. Yes. So actually, the first one, we're only getting the address of variable A, which is in another function, in the main function. Then from that address, we are actually loading twice, the second and the third instruction. Each of this, we are loading 4 bytes to the register EX and EAX. So you can see this one. So this one is a higher address, right? EAX plus 4 is obviously higher than EAX, no matter what EAX value is, right? So this is a higher address. That's why this one is actually loading a higher 4 bytes, not the significant 4 bytes. And this one is loading the least significant 4 bytes. That's why later when we add, this one has a carry, but this one doesn't have a carry. Yeah, when you add
the B value is using ESP.
B value is also on memory, but the value of B is on memory, not the address of B. For A is the address of A. That's why you need to dereference one more time. For the value of B, it's just on memory, on stack, so we directly load that. So if you are still confused about this, it's okay for now, okay? We'll have more examples, more detailed examples later. But if we go to the 64-bit, so the purpose of this is to compare the 32-bit and the 64-bit, so you can appreciate what the architecture has done for us. If we go to the 64-bit, they are compiled from the same C code, exactly same C code. But this one is a 64-bit program. I can prove by, well, file on this. So this is a file command. This command tells you what file it is, right? It tells you this is a 64-bit executable. The previous one was actually 32. So if we do a disassemble this program. Oh yeah, mention J there. There it is. So you can see, first of all, it's much shorter. It actually has 4 instructions. Right? So this one doesn't count. This one is not an instruction anymore because the program already returned here. So actually only 2 instructions. Right? We have a move EDI. So that is the address of A, basically. The variable A's address is in a register EDI. Then we use EDI of the memory address to load the value to RAX. I'm sorry, not EDI, RDI to RAX, and we're directly loading 8 bytes because the register is 8 bytes. So here is Q forward 8 bytes. Then the second parameter B is not stored on the stack. Previously, we're getting the value from stack, EXP plus something, right? Now that value is directly in the register RSI. And the first 8-byte A is in RAX. The second 8-byte is in RSI. Then we just use add instruction to add them together. That's it. Then we're done. Okay. Then we return. So only 3 instructions. So you can see the same C program, but the 64-bit version obviously much faster. We have fewer instructions. The registers are longer. But the program itself, they're not necessarily longer. You can see that this instruction itself is only 3 bytes, 4 bytes. Previously, the other example, maybe the same thing. So that is the difference between a 32-bit machine and a 64-bit machine, especially for the Intel architecture here. So I also want to introduce you a little bit about other architectures, especially I work on ARM. All of your phones, or if you are using a new Mac, you probably are using an ARM CPU there. Your iPad, definitely using an ARM CPU there. They are not necessarily manufactured by ARM. It could be manufactured by Qualcomm, but under the hood is an ARM CPU. So ARM CPUs, they follow the reduced instruction set design. And one thing you can notice that is there are many general registers. In the previous example, the 32-bit, we only have 8 general registers, 64-bit, many more, maybe 16. But this architecture, you can see here, we have at least 30, 31, 32 general registers. And all those registers are 64 bits. Then they have many different special registers as well. So this is the Cortex-A, which are used in our phones, iPad, those kind of high-end consumer devices or embedded systems. Then we have some low-end IoT stuff as well, like those kind of mouse, right? The mouse here, this kind of pointers, those remote speakers, they probably run a Cortex-M CPU. M CPU, they are called microcontrollers. Those CPUs do not have memory virtualization. They don't have a memory management unit, MMU. They have, compared to the previous one, you can say they are much simpler. In this case, only 16 general purpose registers. But those devices right now are very, very popular. We have hundreds of millions of those CPUs in the real world. Okay. Hundreds of billions. They are very, very affordable. Some of the CPUs are like 50 cents. Okay, the whole device may be much more expensive, but the CPU itself is only like 50 cents or $1 to $2. Yeah. So those devices, they were deeply embedded before, so no one worry about their security. But now they are connected to the internet. I don't know if you have a Nest controller, right? So that is Cortex-M based, and you can use your app to control that. It is connected to your Wi-Fi network. A modern car has like hundreds of those devices, CPUs, and they're connected to the CAN bus. The CAN bus may connect to our Wi-Fi, 5G. So that's why people can remotely hack into cars. So one of my research directions is on how to secure those devices. Because they don't have many of the hardware features we take for granted for your desktop, for your servers, then how can we secure the software system with all those hardware features? That's what we do for those kind of systems. So next, we will talk about the Linux file system. The reason, especially the file permissions. The reason we talk about this is I want you to understand how our hacking platform works. You need to understand why it's hard to cheat on that hacking platform, how it is designed. Okay, if you find a way to cheat, but do let me know. Okay? So on Linux or Unix-like systems, there are many different permission groups. So basically, each file or folder or directories has 3 user-based permission groups. Those are 3 groups. One is called owner, another one is called group, the third one is called others. So an owner is the owner of the file or directory. So usually who creates the file becomes the owner. And the owner permissions apply only the owner of the file and the directory. Then there is a group. A group can contain multiple users. All users belongs to a group will have the same access permission to the file, and the group permissions applies only to that group. So everyone else on the system, then they have the others permission. So let's say, then there are 3 different basic permission types: read, write, and execute. Then let's say this figure. This is a screenshot from my old ThinkPad. So for any folder your directory you're working on, you can do a list, ls, and you can show all the permissions and all the files there, right? Then that's my home directory there on my old laptop. Then you can see that the first column will actually have 10 columns, right? And the very first one, it's either a dash or a D, right? D here means this is a directory. Dash means this is a file. So for example, I have an app directory. That's why it's D here. And then the dash means this is just a file. Then we have 9 more. Then we have 9 more columns here. That 9 more columns represent the file permissions for those 3 groups. For each group, there are 3 permissions: read, write, and execute. 3 groups. That's why we have 9 columns, right? So the first 3 columns, those are for the user. Okay, so basically it tells the user's permission here. Let's say this column is the user. So everything here, I'm the owner. Sorry, not the user. Owner. I'm the owner, and this is the group. So I didn't create any other group here. That's why the group name and owner name are the same. Then everyone else is just everyone else. So the owner, I'm the owner for everything here. So my permission for each file, let's say the first file is a PDF file. So PDF is not really an executable. It's not a program, right? It's just a file. You need a reader to read that. The reader is that. So this file, I can read it. That's why I have R there. I can write it. but I don't have the X. X means execute. I cannot execute this, right? Everyone in the group have the same permission as I have. They can read, they can write, they cannot execute. Everyone else on this system, they can only read. They cannot write, but they can read. But as the owner of this system, I can change the permissions, of course. Yeah. Then directories, they have the execute flag here. Basically means you can go into that directory. So that explains the 9 permissions for those 3 groups. This one is the next one is the link count. So how many files are linked to this node? So that's why you say the directories, they have a higher link count because they may have different subdirectory subfolders linked to that. Yeah, go ahead.
Just a quick question on the file directory. I'm poking around in the CPF terminal and I'm seeing some files that have an L.
Yes. So that could be L, maybe a link.
Okay.
That's yeah, like kind of like a shortcut in Windows. Yeah.
Okay. Thank you.
So the first thing you notice here is when you log in this platform, what is your username? Your username is not what you registered on the platform, right? So that is only for the web part. So here, when you log in this Docker image, your username is actually CPF. Okay, that's your username. Everyone has the same username, CPF. So you're not logging as the root user, right? The administrator on this platform is root, right? So you can say all the files, they're owned by the root. We have the flag file. For each challenge, the content of the flag file is what you are trying to steal, right? But you're logging as CPF. But the owner of this file is root. And only root, you can say only root can read this, okay? The group doesn't have the permission to read. Everyone else, CPF, the user CPF, belongs here. You don't have permission to read this. That's why if we do a cat here, the cat is, do a cat flag here, it will say permission denied because you don't have the permission to do so. Okay, your goal is to get the content of this flag file, and it is right there. You just don't have permission. Yeah. In this case, group is also root. Basically, no, there's no other group. Yeah. What's special here is each program, we have run several programs. Each program is a set UID program, which I will explain in a minute. And you can say it has a background color there, makes it look a little bit different. This program, the user is root, but you can run it. As the user, as the CTF user, the owner is root, but as the CTF user, you can run this program. But when this program executes, it will inherit the owner's privilege. So it will use inherit root privilege. Okay. So this program actually has a permission to read this file. So your goal is to hack this program to make it output the content of this flag. So all the challenges are designed this way. Going back to here. So that is the owner field, there's a group field. Then that column basically shows the size of the program. When that file was last modified, and the last column obviously the file name of this program. Not program, the file. So next we talk about the set UID program. How many of you heard about the concept before? Set UID program. So this is kind of like a concept specific to Linux or Unix-like systems. So Windows doesn't really have this. Okay. Windows choose a different design. So go back to our how do we compile a C program to an executable, then have a process. In the last step, the operating system needs to know the program from hard disk, from persistent storage to memory, and execute that, right? To create a process for it. And in that step, the OS will set a lot of permissions and also user IDs for that process. So on Linux, each process has 3 UIDs associated with that. They are called real UID, real user ID, and usually this is the UID of the user or process that created this process. Right? Then there is an effective UID, and this is the UID to evaluate the privilege of this process. So usually for regular programs, the real ID and effective ID, they are the same thing. Okay. So most of the program you run there, they will have the same real ID and the effective ID. If you are running that, then that will be your ID, right? So in this case, you on our platform is the CTF, user CTF, not the user root. Then there is also a safety UID, but we're not using that in this class, so we skip that. So for set UIT programs, they are a special type of program. So in the file system, you will mark some of the programs, they are set UID programs. They will look a little bit different. So for all other programs, like I said, when they are launched, the effective ID, UID, and the real ID, they are the same. But for set UID programs, they are not the same. For set UID programs, the effective user ID is the owner of the program, not who runs that program, okay? So the previous programs, when we run that, we run as the user of CTF, but the owner is root. If they are not a set UID program, the effective UID will be CTF. However, because they are set UID programs, the effective ID actually is the owner, okay? And because of that, so the operating system will evaluate the permission of the program using the effective ID, not the real ID, okay? There are many set UID programs in a Linux-based system. One of the homework you are going to do is to find out what set UID programs or set group ID programs are there. They are actually very similar. So I guess many of you used SU before. You use Linux. If you use Linux, you probably use the SU command, switch user, right? Or there is another one called sudo, switch user do, and to give you root privilege. So those programs are set UID programs. This one to mount or unmount something from the file system is also a set UID program. So if you do a LS here, the difference set UID program is marked in here. So other programs like sleep, this program is executable for everyone. There's an X for everyone, for root, for group, and for everyone else. Okay. But for set UID programs, this one is not marked as X, instead it's marked as S. Okay. Means this is a set UID program. So the shell we are using will actually show a different background here to make it more stand out. So the L you ask here is L. This is like a link, a symbolic link, and like a shortcut in Windows, which means this one is not really a file here. It's just a shortcut linked to another file program. Okay, now let's look at one example. This example is called read secret. We have the main function. In the main function, we have a file pointer. We're trying to open a file. We have a local variable, a buffer. 100 bytes at the C code level, 100 bytes. Then we first get the UID of this program. Like I said, there are multiple UIDs, the real UID, the effective UID. So the get UID, this function will give us actually both, I think. Yeah, the get PWUID will give us this one only give us UID, which is like the real ID, the real UID. So then we print out the real UID and we also print out the name, right? And then we get the EUID here. This is another API provided by the operating system. Then we print out the EUID here. Then we just have a function to print out the flag, right? So the flag, you already know that. There's on our file system, we have a flag file. That's a secret, right? So we simply just read that file and print it out. That's it. Yeah. So that is a print flag file. So go back to our platform. Read secret. So when you run this program, it first print out who is the real user. In this case, the real user, real UID is just user CTF, because we are running this program as the user CTF. Okay. However, because this is a set UID program, the effective user here is actually the root. And because it is a root, now you have the permission to read that file flag and get the string, right? But if you just do a cat here, if you just do a cat flag here, you will get permission denied, okay? Because when you do a cat, why cat cannot do that? Because cat is not a set UID program, okay? If cat is a set UID program, you will still be able to do that, right? No. So this will be your first flag actually. So what you do is you can copy this flag, copy that, then you go back to the challenge, then you go to the web system, and you can submit the flag in this dialog box. Then from the back end, I will know that you solved this challenge. Okay, so that is what you need to do in the homework and also in the hacking CTF communications. Yeah. You guys need a break? So our class will end at, we still have 1 hour, right? Almost an hour. But we still have like 6 pages of slides. So okay. So next thing is talk a little bit about the L file. So L file is the standard format for executables and also for object code on Linux. They can also be libraries, core dumps. So there are many possible extension names for L files. If you use Windows, you're familiar with extension names, right? So on Linux, on Windows systems, the extension name is actually very important. They associate different operations with the extension name. If the extension is .exe, means that it is executable. Then Windows, you double click that, Windows will execute that, right? Linux not necessarily do the same thing. That's why the file names, the extension names are not necessarily associated with an operation. So that's why for L files, we have many different extension names. By looking at extension names, you do not necessarily figure out what file it is on Linux. For example, there could be a .bin file. Bin, it's just binary. Some of them just the .l file. For embedded systems, sometimes we compile firmware, everything. It could be .bin file, .axf file. Then .o file is object file. You have compiling C code, so you know that. There are many. KO is usually a kernel module. So it's like object file for the kernel. Mod is also a module. SO usually is a library. S is a static. That's a library. And also I see .a is the library as well. So L file contains programs and also data. Also describes how programs should be loaded, and also contain all kinds of metadata describing the program components. So the equivalent file format for this on Windows usually is called a PE format, portable executable format. So on Linux, you can use the file command to learn what file it is. Let's say we use ls, which is a command. The command actually behind the same, there is a program for that. So obviously that is an executable file. So then you can do a file on that. When it tells you, oh, this is a 64-bit shared object, and this is dynamically linked. To load this one, you should use this loader, interpreter. This is the loader, and this is the hash value for the program. And there are not much symbols left, so this is a script, right? So the file, obviously, you can use this command on everything. Let's go back to just this example. Let's see what we have here. We can do a file on the flag file, let's say. What will happen when you do a flag file? It says this is just a regular file, but we don't have read permission. So it cannot really tell us what it is. Then here's another file. Docker environment. We have to this one. It tells us, oh, this is actually empty. Nothing is there. And you can see that the size of this is 0, right? Here we have a script. This is script you will use in the future. The file tells us this is a shell script. Basically, everything there is just ASCII, it's text, but at the same time it's script, so it's executable. And if we do the read secret program, it tells us this is a 64-bit step UID L file, right? And this one is actually not strict. You can say it's not strict. The previous one on my slides is strict. Not strict means there are a lot of symbols, right? The debug symbols are still there. But if we do an M there, we should be able to see a lot of symbols. Yep, we see all the symbols there. The function names, the variable names, they are here. So there are different sections in an L file. The read secret is an L file. We can do a read L. This is a tool, read L. This tool tells us a lot of information about this L file. Let's say a lot. Let's start from here. Okay. So first, it tells us this is the ELF header. What are the magic numbers? What class of this ELF file is? 32-bit, 32-bit converted for Linux or Unix system V, what type of file this is. This is a dynamically linked shared object file. The machine is for 64-bit of AMD or x86. This is another interesting thing is when we talk about x86, it was invented by Intel, right? And that's 32-bit. However, when we talk about x86 64-bit version, that instruction set was actually invented by AMD, not Intel. That's why we say AMD here. Then we say, where is the entry point? That is the function address. So that's probably the start function. Let's verify that. So here the address is 11D0, but obviously this is the offset, right? This is not a runtime address. So 11D0 probably should be the start address. See here, okay? The start. That is the first function. That's a function not, that's underscore start. That's a lot of function you develop. That's a C library function, but the OS will give the CPU the control flow to that function. So that is the first function executed in the program. So this address you can see is starts from 000, very small address. So this is still an offset, not a runtime address. But you can see that the entry address, the entry point for this program is this address. Then it shows where is the section headers, the size of header, how many sections, how many segments there. Then we have the section headers. There are many different headers. Dot interpret for the interpreters. Then what kind of permissions this section have. There are different sections. You don't need to remember all of them. Some of them will be important for us. For example, this dot elite. That obviously has the initialization functions. PRT, we'll talk about this as well. Dot text. Usually your program, okay, your C code after compilation goes to this dot text section. That's a code section. There is RO data. Can anyone guess what is RO? Exactly, read only data, right? So some of the data you can read and write. Some of data, like macros, it's just the read only. You're not supposed to change that. So that's why there is also data section, right? So there also is BSS section. That is a section for uninitialized data, right? So uninitialized variables, they go to the .bss section. So .data section, those are for initialized data, global variables. Because they are initialized, which means in the program, in the L file, you need to record the initial value of them. But for BSS data, they are not initialized. So you don't need to record their initial value in the L file. And in C standard, they should always have the initial value of 0. Okay. So the loader will not load the initial value from the L file. They are not there. The loader will just set their value as 0. That's it. There's common section, many other sections. So several sections I think are very important for us is .text section. This is the executable code. Then .prt, .got also important for us. I will show some demos next week or maybe this week. Yeah. .data section is for initialized global variables. RO is for read-only data global variables, something like the strings. BSS for uninitialized global variables. So obviously, local variables are not here. Okay, local variables are on the stack, so they're not stored here. Many tools for us to analyze L files. We actually have used several of them already. Okay, so GCC, we used it. Okay, that's a compiler. Turn your C code into an L file. In our research, we also use LLVM as a compiler a lot because we can easily change LLVM, but it's harder to change GCC. So my PhD students, one of their job is to write all kinds of LLVM process to change the compiler. Then the readelf, the tool we just used, this one can tell you a lot of information about this L file by reading the Elf header. We already used the obj dump. Okay, so this is a simple tool for us to get the disassembly. We are going to use this will be our friend this semester because we're going to look at this assembly, find the vulnerabilities. NM, view the symbols I just showed you. We can also patch Elf to change some part of our Elf file. OBJ copy, we're going to use this to copy part of the sections. When we develop shellcode, we're going to use this tool a little bit. Strip to remove other symbols. Obviously, there are also APIs to do this, and also a lot of tools with GUI. But in this class, I want you to use those simple tools. Okay, next we talk about the memory map of a Linux process. So Linux is a multitasking operating system, which means you can run many different applications at the same time. Same as Windows, same as your Mac, right? Then from the OS class, you know that we have this for each application running on top of operating system. We usually give them an illusion that they have full control of the hardware. They have the full control of the registers, but we only have one copy of those registers, right? The operating system is providing that kind of virtualization or illusion to the operating system, to the applications. So we can call that illusion also a memory sandbox, but it's not only a sandbox for memory, but also everything else. So this sandbox is a virtual address space. This is achieved using the memory management unit, MMU, which is a hardware feature in the CPU. About the operating system, we utilize that hardware feature. If we are talking about a 32-bit machine, then the virtual address space will be 2 to the power of 32, which is 4 GB memory space. Okay, that's not very big. 4 GB is basically 4 billion, something like that, right? So those virtual addresses, eventually they are mapped to physical address. Okay. So your physical machine may not have a 4 GB memory. The physical machine, I think right now our memory our laptop memory are big. I think my laptop has a 32 gigabyte memory, but also I'm running a 64-bit OS there. Everything is 64-bit. So the virtual address space technically can be as large as 2 to the power of 64, not 32. For 32, for like 20 years ago, our memory would be 256 megabytes. Right? But even back then, with a 256 megabyte physical RAM, each process, each application, they still have a virtual address of 4 GB. Right? There is no physical memory to back that up, but virtually it's that big. Yeah. So the virtual addresses are mapped to physical addresses by using MMU, and MMU will use page tables to do that. So they are maintained by the operating system and also the help of hardware. So in this class, we're not going to talk about that. So in my advanced software security class, we will touch kernel stuff, we will hack those. So on a 32-bit machine, let me mute my phone here. So on a 32-bit machine, this is what the memory looks like for each process. This figure is a little bit old, okay? So things has changed a lot in the last 15 years, mainly to make the system more secure, and also for 64-bit, much bigger. But the general idea is like this, okay? Even though their order may be a little bit different, but the general idea is like this. So here, and I use this figure because for most of you, this will be easier to understand. It's much smaller, just a 4 GB, and you can clearly see different sections behind it. Let's say the lower address here, this is lower address, that's higher address. Look at this number. The first digit here is 0. This is the lower address, and that's that. This one is C, that's a higher address. So the top 1 GB is reserved for kernel space. So user code cannot read or write to those addresses. If you do that, you will get a segmentation fault. In Linux, you have a bug, you will get a segmentation fault. So right now we do not worry about this one. And let's start from here. At the very beginning, this is the virtual address. At the beginning will be very small memory address, like 0. So what is 0 in C programming? It's null. It's 0. It's nothing. You're not supposed to dereference that, right? Okay. So which means this part of virtual memory address, or maybe just 1 page, 4 KB or whatever, no one is supposed to dereference that. Okay. And that is defined by most of programming languages, like C. Which means this virtual address will not be backed up by any physical memory. Okay. Imagine you only have physical memory. Then of course, you have 0. That's a valid address. But for virtual memory, then we do not map this to anywhere. So any dereference from this will be integrated as illegal. Then we have the dot text segments. So this is where your binary, your code, your machine code is actually stored. Okay. So after that, you should have a dot data section. This is the global variables. For example, here we have a global variable, which is a string, God's own prototype, right? And this is an initialized global variable. So this global variable, this is a global variable. There are 2 things. Here, this one is a string. The string itself is read only. Okay. So this one, the string itself actually can go to the read only section. Then here we have another variable. This is a variable. This variable is a pointer. What is a pointer? Pointer is basically an address. So this pointer should have the address of the string. The string may be stored somewhere else. Okay. And this variable is initialized. When you run the start function of this program, this variable should already have a value. The value is not a string. The value is the address of the string. Okay. Then we have the BSS segment. Those are for global variables that are not initialized. Let's say there is a static char star username. This is a pointer, another variable. This one is not initialized. According to C standard, if it's not initialized, it should be initialized to 0. Okay. So it should be filled with zeros. So the whole part will be filled with zeros. Then we have the heap. Like if you use malloc, malloc is going to allocate data from the areas from the. Then we have stack. That's for each function. They have their own stack. Actually, for each thread, they have their own stack. So actually, we may have multiple stacks here, okay, for different threads. Then this is a memory mapping segment. Those libraries, they are loaded in this region. You load those libraries, use different system calls like mmap. We will talk about that later. For example, here, there is a libc.so. So this is also an L file. And the type here is SO, static library. And this could be a dynamic library, actually. So the interpreter, this is the C library. We'll load this C library to this virtual memory version. You may have multiple processes running, and all of them may have a C library. But this is a virtual memory address. In a physical address, there is only 1 copy of the library. We just map them to each process own virtual address. There's only 1 copy because no one is supposed to change this anymore. Right? So the stack will go down, like we said before, and the heap will go up. Okay. So that is a very simplified memory map of Linux process. So the null pointer in C or C++, basically it's defined as the address of zero, which means you're not supposed to revert from that. But the newer version of C++, they actually changed this, I think, make things a little bit different. But I'm not familiar with the newer version of C++. There have been too many changes recently. So let's take another concrete example. We're going to look at this program's memory map. This is a very, very simple program. It doesn't do anything actually. It will ask for a character, right, from the terminal. Get a chart will ask for your input from the terminal, just one character. So if we do not input anything, what will happen? It will get blocked there, waiting for us. Then we open another terminal to analyze. So the program will not exit. Then we can have another terminal to analyze this program to say the memory map. So let's go to process map. Let's check the 32-bit first. Okay, let's run this program. This program is running. If we input something, it will exit. So we don't want it to exit. One way we can do is we can have multiple terminals. So on this server, we already installed the tmux for you, the type tmux. Then Control B, semicolon, the percentage sign. You get two terminals here. Then on one of the terminals, we run this program. The program running. Now we go to the second terminal here, and here, let's try to find that. Let's try to find that process called map, process map. Right. We do a grep here. You can see that. That's this process map. Right. So we can use several commands to analyze its map. So there's a pmap command. Use PID. So here is a PID, process ID, 2424. Or maybe this one's ID. 58. Yeah, maybe 58 of them. Which one is ID? Let's say, if you want to log, yeah, what? I don't have permission for that one. Oh, maybe exit from the lowercase. No. It's definitely running there.
What and you're using to switch between windows? I'm understanding.
Control B, then just arrow. Control B, arrow.
Holding down the control.
Yes,
key. Okay.
yes. So, um, So X is extended. Uppercase X should show us everything. Is that correct? Um, so PID, okay. So PID is in the second column. So I show you the second column. So it should be 58. 58 is one. But somehow it's not showing me everything. Okay, I need to figure out later what's going on here. I most likely to be a permission problem. If we have the permission, what you are going to say is something like this. You will be able to say there are different memory regions of this program. So this is from very low address. This is from lower address to higher address. So here, this part you can say different memory regions have different permissions, like read, not writable, only readable, and also executable. So this one looks like the code section. Right? So it's mapping the program PM there. I was using a PM program. So this program, the program also is divided into several different regions. And this one looks like dot text. This one looks like read only data because it only has a read permission. This region is only. The next one is read and write, but not executable, which means the sixth one may be the dot data section, right? Then there is P. Then we can say this is the C library, the deep C. The C library also has different regions. There are other areas as well. Yeah. So another library loaded there. There's also stack and other areas. So for 64-bit machine, the same thing. The difference you can see is the address is much longer. Now the address is 64-bit, and we are still mapping those different things: the program, the heap, the library, the interpreter, stack, and also some other regions that mapped into the memory address. Okay, the next part is system calls. This is actually very important. I think I will give you one. I will show you one example of how to make system calls in assembly. We do have example of that, I think, but we will also revisit this part later after you see how to use and export. Okay. So what is a system call? System calls are interfaces provided by the operating system. Your Windows, your Linux, they need to provide a service for upper layer applications. And that service, the mechanism to provide that service is called system call. When you program an application, you do not necessarily directly make those system calls. You make library calls provided by libc or some other libraries. But those libraries eventually will call those system calls. That's why most application developers, they do not realize they're making a lot of system calls. But those libraries, technically, they're not part of the kernel. The libraries are still part of your application. It's still usernet. So whenever you are going from the usernet going to the kernel, you're making system calls. To make function calls, you use the call instruction we just saw. To make system calls, you don't use the call instruction. Okay? There are special instructions to do that. A different hardware architecture may have different instructions. x86, there is an int instruction we use. So system calls enters the kernel performs service and returns then your process, your application keeps running. Then your process make another system call, it enters the server, under the kernel executes, then returns. System calls are generally not invoked directly by the program, but by a wrapper function in libc. That's why sometimes you do not say them. There are many different system calls. I think right now there are hundreds of them. On Linux systems, those are the system calls we are going to use a lot. Open a file, read a file, write to a file. So everything on Linux can be a file, okay? So they abstract everything into a file. So open, read, write, close, then you can do for the files. Then you can wait for another process, execute a new process, you can fork, you can exit. You can also send signals to other processes use a kill system call. There is also a kill bound tool, line tool, right? That's actually also to send the signals. So that tool eventually makes a system call of kill. So you have been using the C library functions like open, read, write, close, right? Those are C library functions. Those are basically the wrappers of those system calls. Linux probably have more than 300 system calls, maybe even more. Windows 7 has maybe 700 system calls. Yeah. Usually, for most of the system calls, the C library, the libc, has a wrapper function and usually has the same name as the system call itself. For example, if you want to change the directory, you would ch change dir directory. Eventually, this C function call calls the system call of change directory system. Okay, let's say one example here. Another very simple program for the first flag. This program doesn't do much. It just print out the flag for you. That's it. Okay. This is the setuid program. It reads the flag, print it out for you. Okay. So it will just print out congratulations. I'm getting your first flag. Then print out the flag. And the print flag is the function we just saw. Okay. This function will use the C library function fopen to open that flag file. Then check if the opening is successful. If it is yes, use fread, read the content of that file to the buffer, then just use printf. Then to print to the terminal, then just close. Okay, the file. That's it. Okay. So how many system calls you think this program will make? From here, you can say at least there should be an open system call, right? There should be a read system call. The print, okay? There's no printf system call. It's actually writing to somewhere, writing to a file. Okay, right now the file is basically the terminal, right? So here, at least there is a write system call. Okay, then the close, that will be a close system call, and there will be another write. Okay, so looks like that's a system calls running. But actually, this program will make many more system calls than that. So to trace what system calls this program use, you can use the strace command to do that. If we go to the first flag, we go to the first flag program. When you run this you get a flag. You can do a strace on this. Then you can see what system calls this program has been making. Okay. So let's go through each of them to say what this program is doing. Okay. So many of you developed a shell before. I think we talked about that. So this is a shell, right? The shell, you can type some commands. So what does a shell do? The shell will actually create another process. How do they create another process? Which system call or function use? Fork, right? So when you do a fork, then you will have two processes, the old one and a new one, a child one. Then in that child process, you will do exe to execute the new program. In this case, the new program is this first flag 32-bit. Okay? So before exe when you call that fork, you call that in the old process, right? The share process. That's now here we're tracing the new program. That's why you do not see the fork here. You don't see the fork, but you do see the exe here. Okay. So in that exe what you say here is we're going to execute this program, right? And those are the arguments for that program. It could be environment variables, those kind of stuff. So we'll cover that. I don't know if we have time today, maybe later. Then we have an access system call. This is system call access. This one will actually check if this program has a permission to read this file. And it says, oh, this file doesn't exist. Then there is a break system call, BRK break. That is to adjust the heap, okay, the data segment. If you do not put a value here, you just give 0 here, it will returns where the heap is, where the data segment is. Now, so if you develop an operating system, those are the interfaces you need to develop. As long as you develop those systems, those system calls, then other applications can be easily migrated to your operating system. You know? So if you took an operating system class, those probably the interface you develop. Okay. Then there is architecture control stuff. This is to set our architecture something. Then there is a file. F usually means file control. Those three are interesting. Okay. Those three. So 0, when it returns 0, you say means it's successful. When it returns an elective number like this, -1, it means it's not successful. Okay. So here, it's actually setting the first 3 fire descriptors. Okay. So in Linux for application, usually we have multiple fire descriptors. The default one is 0 for standard in, 1 for standard out, 2 for standard error, right? Now we're collecting the terminal to that. That's why we're using standard in, standard out, standard error. All of them are connected to the terminal. So this is making the connection there. Okay. Now this process has file descriptors 0, 1, 2 for the terminal. Okay. Then we're trying to access this file doesn't exist, this one doesn't exist. Then we do a memory map. The memory map is try to reserve some virtual memory address or load some libraries into the system. So the memory map, there are actually 2, a memory map and memory map 2, similar. Then we have an open. So this one is try to open a file. So open at is basically a variant of open. Okay. So we open this file. Look at this file. Loader SO preloaded looks like a interpreter or loader. Right. Trying to load that, and it was actually successful. Great. Loading that. So after that, we check the status of a file. We memory map something else. I'm not sure we're memory mapping here. We don't know yet. So then we close the file descriptor because we opened it somewhere. Here we open this. Previously we have 1, 2, 3. Okay, those 4 file descriptors and for the terminal. So now we open another file. Then you will have a file descriptor number 3. Okay, after we use that, we close it. That's why we close 3. And we check this file again. Then here is we're actually trying to load the library. Okay, we're open at the C library, libc library, and after that it returns the file descriptor 3. Previously also returned 3 file descriptor. So the open system call always give you an available file descriptor with the smallest number. So here, because 0, 1, 2 has been used, so 3 is the smallest number. Now we close it, so 3 is available again. That's why now we have 3. Now we're trying to read that library, right? We read that 3, we're reading that C library, and we're probably loading that into the memory. So here we are basically reading that memory. I think this one is trying to load that C library into the memory. And this is probably the C library address here. Okay. After that, we change the permission of change the permission of that address. So C library has multiple parts, right? Has code part, has data as well. So the code should be readable, executable, but not writable. Data should be writable, and this M protection is to try to set those permissions. Okay. So I think those are probably loading different. Yeah, see, well, it's still loading from 5 descriptor 3. So we're loading different regions of the C library using the memory mapped system call. Now after that, we close this. So even before here, we haven't touched our own code yet. Still is a C library, the interpreter is doing this. Let's say where we have our program. Starting from here, that's our program. Our program, the first thing we do is we print out congratulations on blah, 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 right? So that is actually the printf eventually makes a system call or write system call right to the terminal, right to the standard out, okay? In that case, the file descriptor is 1. That's why we have this system call. It's successful. It returns how many bytes we write, 45 bytes. Now after that, we try to open the flag file, okay? And we do have the permission. Oh, when we do strace, we don't have a permission. Okay, that's why. But when we do strace, it's not a set UID program anymore. Okay. There are some settings we can do to make it still trace it, but in this case, it's not. That's why this permission denied. Okay. So then, in this case, it's write arrow cannot open the flag file. Otherwise, it will print out the flag. So, see here. Well, we cannot open that file, it will put arrow cannot open the flag file. So strace is a tool you can use. So in the CTF and also the homework, sometimes I will just give you a binary. And the first step is reconnaissance. You need to figure out what does this binary do, right? Fitting what does this binary do? And what kind of input this binary takes. Imagine you want to hack something. How do you hack something? You have to feed it with some data. Then you need to figure out where it takes data, where it takes input, right? So strace and other tools, that's what you need to use to figure that out. So here is a list of the system calls here. I have a little bit information for everything. So if you see a system call and you're not sure how to what it is for, you use the man command. Okay, so the man command on Linux is for the manual, the descriptions. So the manual for Linux has many different sections, and section 2 is for system call. Let's say if you do a man open, then you will look for the manual for open, but here open could be a system call or could be a function call, right? In this case, you choose true, means this is a system call section, and those system call are actually wrapped up by those functions. So let's say we have unmap. So not unmap, what was it? It should be M unmap. M means memory unmapped. So this one we're unmapped a memory region in the virtual address space. And right, please not forget. Oh, unmapped. There should be an N here. So when we do this, you can say, how can you use this system call? And also there is a C library function for this. And how do you call this at C level, which is equivalent to system call. So I think we probably have 2 more minutes to talk about how to make system calls at binary level, at the assembly level. Because in this class, you are hackers. You don't have the luxury to write C code. You are just sending raw bytes. So you need to write assembly a little bit. But for most of those, I will give that to you. But at least you need to understand what they are, right? So on x86, the system calls rely on software interrupt. And the software interrupt is caused by a special instruction, which is the int instruction, okay? Int, that's an instruction. And that instruction takes one operand, which is the interrupt number. And on Linux, the interrupt number for 32-bit, the interrupt number 80 in text, that is reserved for system call. There are many other numbers, but and also there is also later introduced a new instruction just called syscall. Okay, that's also introduced in 64-bit. You can only use this instruction. There are other numbers for different interrupt. For example, in Windows, I remember at least the older version, they reserved the 21 in text for system calls, but not the same number. That is an interrupt number. Then we have, we already said for Linux, maybe 300, 400 system calls, right? Then each system call have different parameters. For example, if there is an open, then you need to the file name for the open, which is a string, the address of that string. Now, how do you want to open it? What permissions you want to have, right? So here is the link from Google for all kinds of system calls available on different architectures. And at the beginning of the class, we're just using this table, x86 32-bit. Later we'll use 64-bit well. For my research, I use a lot of ARM 64-bit. Yeah. So we can say the system call here, let's say. So the instruction is always int 80. Now, how do you know what system calls you are making? There's so many systems. You basically put a system. Go ahead. Exactly. You put a system call number in the EAX register. So the EAX has the system call number, like the exit has a system call 1, fork has a system call number 2. They are supposed to put that number in the register. Then each system call, they have different parameters. For fork doesn't have any parameter, you just create another process. So you don't need to set any other registers. The kernel doesn't care, okay? If it's a read, then you need to put what file descriptors you want to use to read from, and where is your buffer, and how many bytes you want to read. And those should be put on different registers. Read is the third system call. 3 goes to EAX. The file descriptor you want to read from goes to EBX. The address of your buffer, this is the user space buffer address, goes to, this is the address. The address goes to ECX. How many bytes you want to read, go to EBX. So that's a basic idea of system calls. So when you develop shellcode, you need to search for this table and search for the system call you want. I guess we don't have time. So Thursday, we are going to take a look at this piece of shellcode, and we are going to look at it one by one, the instructions one by one, and figure out what those 9, 10 instructions do here. And at the end is making a system call. Okay. So this is part of the share code we are going to use. Any questions? We're good? What?
One good question.
Okay, go ahead.
I have a lot of questions.
Sure.
So first, we have a lot of registers.
Yeah.
And when we run the C program, we cannot control the register directly, right?
You don't. You can. In C, well, that's the beauty of C. You can do whatever you want. You can embed assembly code in your C code. So you can manipulate the registers. So some of the challenges I do that to make it easier for me to develop the challenge.
Okay, so they just, okay, I got
You,
it.
you Google, embed assembly in C code, you can figure it out. Yeah.
And also I have a question related to the keyword. What is keyword and keyword in the assembly?
So Q means, quad,
What?
8 bytes. Q word means 8 bytes. Keyword means double, 4 bytes.
Okay,
So that specific example is because there is an address there, and you don't know how many bytes you are loading. That's why you have to, in that assembly language, you have to explicitly say that I'm loading 8 bytes or 4 bytes by using the keyword or keyword code.
and why is the 64-bit machine's assembly code shorter than the 32 machine? Like you show us the app.
Yes, I don't really know. I mean, the developers get smarter.
So every time you add a long, it's forced to use the few registers and then add them to the registers.
Yes, I think you're asking the program is shorter or the instructions are shorter.
Oh, the instruction.
He's probably asking more like for specific instruction, why it's shorter, right? Well, he answered that why the program can be shorter.
Okay.
For the instructions, it's actually a coding problem, right?
Mhm.
So yes, so it's a coding problem, right? So then I don't know if you took information theory or whatever. Then when you do coding, there are a lot of tricks you can play, right? For what's that, Hamming distance coding or whatever. So for instructions that you use very, very often, you make them shorter, right? So then in general, your program will be shorter.
And also I have a question related to the link.
Yeah.
What is link? What is link count?
Link count. So for example, is a directory. The directory in Linux, it has subfolders
Yeah.
and files in that.
Yeah.
And the link count tells you how many files
Okay,
are in that directory.
so basically it's a directory, so we have link. Like for.
Not
and
only for directories, but also for other file types, like
other file
like a symbolic link.
but like for script, we don't have any.
For what?
A script.
For a script, it's just if you're talking about a file itself by itself,
A file.
it's not linking to anyone else. There is no shortcut. There also it doesn't have a sub file, no sub concept, right? Then in that case, it's
don't have.
no, yeah, it's just yourself.
And why do we use that UID program?
For many reasons, sometimes we want to. We need those kind of programs to do something special for us, actually. Let's say if without that, you cannot have the SU program, then that's actually a very good question. So I don't have an answer in my mind right now. What I can tell you is there could be other designs to bypass the SetUID design. Like I said, Windows doesn't use the SetUID philosophy, okay? But it will make things much easier for us.
What is the advantage of?
It's a big question. I don't have the answer for you right now. Yeah. Yes. Do some search. Yeah.
Okay.
Yeah.
And what is tag segment in ELF?
That's where we put the code, the machine code. Yeah.
Machine code.
Yes.
And I think like, is it 4 GB for a memory map of a?
That's a virtual memory for 32-bit. Yeah.
Is it too large for?
If you think about it, it's very large, but not every byte in the virtual memory address is actually mapped in the physical address.
Oh.
It's actually, the real data is scattered somewhere. A huge portion of that memory address was never mapped. They're never used.
They never do.
Never used, yes. If you want to map everything, the page table will be huge. Yeah. For the operating system side, the page table will be huge.
And the last question, why do we use trace?
Use what?
Trace. TSPRAC. Trace. the command.
PR,
It's
or asterisk. That is the program for you to, that's a tool to show you the system course the program is making. Yeah.
But how do we write?
So for a program that you are going to hack.
Yeah.
What is the first thing you want to do? You want to run the program.
Sure.
You want to say what the program is doing.
Okay.
And the asterisk can tell you kind of like a digest, what system calls this program is making, right?
Mhm.
To help you better understand the program.
Okay. Yeah, I think that's all.
Cool,
Thank you so much.
sure, good question.